Hi Alex, today I'm going to talk about our motor control platforms, and the first demonstration platform here is focused very much on isolation architectures. You can see a board here. This is our inverter platform. It contains isolated gate drivers for 6 individual IGBTs. It also has some isolated ADCs for current feedback. And if you see on the screen over here, we have 6 gate drivers there, 2 ADCs. These are isolated sigma delta ADCs. So they measure the current, the voltage across that resistor for current feedback. They send a digital bit stream into that controller that includes a sigma delta sync filter that reconstructs that current signal. So this is giving you current feedback and then voltage drive. Now you'll also notice in that diagram that there is an isolation layer between the control and the user interface. Now this is something we're seeing more and more in drive systems, because they would like to customers would like to shrink down the isolation components and have just functional isolation on the power board so they can make a very small inverter. And now they will have a control processor that's doing motor control and have either a backplane or a connector to another board that's doing the communication interface. Now in this demonstration, the communication interface is just up to the PC. But in many cases, that could be a very high-speed communication to synchronize multiple motors, say in a robotic machine or some assembly machine. So what we're looking at here is the new ICs out in the past few months that are isolating an LVDS signal between these 2 control processors. This LVDS isolator can isolate up to 600 megabits per second of a signal, so you can get a very fast serial interface between these 2 boards for high performance systems. So that's the hardware aspect of the control system. Now when we come to this side, we're looking at some of the software issues in motor drives, and one of the things we've focused on here is what affects closed-loop performance of a drive system. And looking here, we're plotting the frequency curve of the torque. You have a fundamental and various harmonics. And torque ripple is quite important in automation drives because it guarantees, how well or how smoothly you're controlling the system. That'll affect quality. May affect the bandwidth that you can drive the system at. So you want a low torque ripple. And it turns out the way you measure the current in terms of how you sample it and the offset in the converters can have quite a big effect on that torque ripple. And this is a system we used to determine this. So we study this. There's actually a paper presented today at PCM on this. So we have a motor drive, a torque sensor, and a load. What I'm going to do is try to start this. Okay, Alex. So I'm running this motor here at about, go to something useful. It's about 800 RPM. So at the moment we're seeing a curve here that has the fundamental. This is a ripple component due to the mechanical setup. So it's a twice per frequency. And then there's not so much ripple, there are much lower components then at the higher frequencies. And in this configuration you have 3-phase current measurements, which happens to be very good at self-correcting for offset drift. Very commonly you'll just use 2 current measurements. Now in that situation the offset don't cancel because you're measuring 2 currents and it's a common mode signal. So if I get rid of the 3rd current signal here, I'm going to do that in software. I introduce this major ripple component. So now we get a significant ripple added, and that's going to degrade the performance of the system. So this is a means of studying, what happens, and it helps us having conversation with customers about how they link component specs back up to the closed loop performance. I think